In this video, we're computing the total energy it takes to pump all the water out of a cylindrical water tank by pumping it over the top edge of the tank. Now in calculus classes, these are often called work problems, but I actually gave this problem to a physics class, so the style of the solution is going to be a lot more like what we do in a physics class. And we're actually going to stay symbolic all the way through the final solution of the problem before we plug numbers in, because there's a really important thing to notice about the symbolic solution to this problem. In fact, at the end of the video, we'll see that there's a simple trick with the center of mass that would allow us to answer this problem in one line. So watch to the end if you want to see that center of mass trick, but for now we're going to directly attack the problem with integration. So we're given a lot of specs in the problem. We're told that the total height of the tank is 1.5 meters and the depth of the water is 1.25 meters. In the original statement of the problem, we were given the diameter of the tank, but I went ahead and divided that by 2 already because I'd rather talk about radius. So that's 0.25 meters. And then we're left with a gap above the surface of the water of an additional 0.25 meters. So the basic strategy of the problem is that we're going to slice this water into thin disks that have an infinitesimal mass, and we're going to compute the total gravitational potential energy increase for each of those disks to get them to the top edge of the tank. And then we'll add up those potential energy contributions for every disk of water all the way from the surface down to the bottom of the tank. So this is a representative disk that we've labeled with a mass of dm. So it's an infinitesimal quantity. And we've identified the position of this thing with a new variable x, and that's the distance that disk is below the top surface. So as x goes from 0 to d, remember d is the depth of the tank, we're talking about disks all the way from the surface of the water to the bottom. Now before we get started on setting up our integral, I think it's a good idea to have a reminder about density. So we normally use the Greek letter rho for this, and density is the mass divided by the volume. We can always turn this around and say that a mass is computable by taking the density and then multiplying by the volume. Well, this is also true for an infinitesimal mass. So we should be able to write down our dm as the density, that's just the density of water here, multiplied by the volume of dm, which is an infinitesimal volume that we'll call dv. Now we can express dv in terms of the parameters of the problem. That's the volume of that little infinitesimal disk. And all I have to do there is take the area and multiply by the thickness. So that's pi r squared. And then the thickness is a small increment in x that we'll call dx. So now we can get to work on finding out how much gravitational potential energy increase is needed to take that little disk of water and move it to the top edge of the tank. And remember, gravitational potential energy is given by mgy. And the increase in this gravitational potential energy is going to be the mass of this disk times g, that's the acceleration of gravity, times the change in height that we have to move it through. So this time the mass is dm, it's an infinitesimal mass. There's our constant g, and then I need to write down the height that we had to move it through, and that's just h plus x. Now we can just sub in our expression for dm. And there I just directly replaced dm with rho pi r squared dx. We're going to rearrange things a little bit. So I'm moving all the constants out in front and kind of organizing those as rho g pi r squared. And then we have an h plus x dx. So now that the potential energy increment is phrased entirely in terms of a single variable, we're ready to add these up by using integration. So we say the total potential energy increase that it takes to pump out this tank is equal to the sum of all of those little potential energy increments. And now we just sub in our formula for those increments. I'm going to move the constants out in front as I work, and I get rho g pi r squared times the integral of h plus x dx. Now the limits of integration here have to cover chopping this water into disks all the way from the top surface to the bottom of the tank, and that's as x goes from 0 to d. So the constants out in front are just spectators here. And when I integrate h plus x, I get hx plus 1/2 x squared. And I want to evaluate this from 0 to d. Now when I replace x with 0, both of those terms are 0. So I don't have to worry about that part. All I have to worry about is subbing in a d here. And we arrive at a symbolic solution of rho g pi r squared times the quantity hd plus 1/2 d squared. Now there is some value in factoring out one of those d's. So I have rho g pi r squared times d times h plus 1/2 d. And I'm going to put a box around that because that's really the final symbolic solution. So now we can just plug all the numbers in and find out the actual amount of energy it takes to pump out this entire tank. But remember, at the very end, we're going to take a fresh look at how to do this by using the idea of center of mass. So when I plug numbers in, I have 1,000 for the density, 9.8 is an approximation for the acceleration of gravity, and then I have a pi in there. And then I have an r squared, so 0.425 squared. And we'll just continue down here. Then I have to multiply by the depth of the water, which was 1.25 meters. And then multiply that by the quantity h plus 1/2 d. So that's 0.25 plus 1/2 times 1.25. And when I run the numbers on this to 3 significant digits, I get 6,080 joules. Now, as promised, I wanted to present a clever alternative solution that takes advantage of a theorem from classical mechanics. It turns out that the increase in gravitational potential energy for an extended body depends only on what happens to its center of mass. Essentially, we can pretend all the mass is concentrated at the center of mass, and then solve this problem by finding out how far we have to lift the center of mass to get to the top of the tank. And I'll post a link at the top to where this theorem about gravitational potential energy was first proven. So what I want to do is just identify the location of the center of mass. And because this tank has a uniform cross-section, it's simple to find the center. That's a height of d/2 above the bottom and d/2 below the surface of the water. So this is our alternative solution. We're going to take all the mass, I'm just going to call that capital M for now, and then multiply by g. Again, just using the fact that gravitational potential energy is mgy. And then I need to multiply by the change in height for this center of mass. Well, we have to go up by d/2 to get to the original location of the surface, and then an additional h to get to the top of the tank. So I end up with this expression, d/2 plus h. And then we realize this is exactly what we were looking at when we did it the long way. The total mass of the water is just the density times the volume, but the volume is pi r squared times d, and we end up with the exact same expression without ever having to calculate an integral. Of course, when we plug our numbers into that, we get the same numerical answer, which is 6,080 joules. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.